A shorter version of this post was published in Palladium on October 18, 2024. This version incorporates helpful feedback from a number of knowledgeable readers. With the recent SpaceX Starship orbital flight tests, it is time to commit to building the largest physically possible space telescope. Such a telescope would peer deeper into the universe than any before it, answering fundamental questions: are we alone? What do Earth-like exoplanets around other stars look like? How did we get here? What weird stuff awaits discovery? Where is the limit on human ambition to know what is in our universe? The Monster Scope answers these questions. Monster, because of its enormous scale, grotesque in its ambition. Monster, from the Latin root for revealed thing. And monster, because through it we can study the life forms, both monstrous and marvelous, on distant planets. Image: SpaceX. When we look up into the night sky, we see thousands of stars. Most of them, visible to our weak and poorly evolved eyes, are either exceptionally close or exceptionally bright. Along with the starlight that passes each moment through our cornea onto our retina, its brother and sister photons splash uselessly onto the skin of our face, the ground around our feet, and the rest of the entire planet. A telescope gathers this wasted light, corrals it into exquisitely sensitive instruments, extracting more of the ambient information that otherwise flows unseen and unstudied around us. The larger the telescope, the smaller and fainter the things it can see. Our pupils are but a few millimeters across, while the James Webb Space Telescope, JWST, 1,000 times larger, can see objects millions of times fainter. For telescopes, a simple rule applies: the bigger the better. Since Galileo first used a military telescope to study the heavens, telescopes have followed a sort of Moore's law, doubling in size roughly every 50 years. There is no reason we should be limited by historical precedent. We are, collectively, much richer and more capable than our ancestors. We are curious, motivated, wealthy, and now thanks to SpaceX, we have a really big rocket. Basic diagram showing relative resolving power at various distances of various telescopes, including the ability of the Monster Scope to bridge the interstellar distance gap. Bigger aperture is better. WISE has an aperture of 40 centimeters. Spitzer has an aperture of 85 centimeters. JWST has an aperture of 6.5 meters. Historically, new space telescopes have been as expensive as they are infrequent. Despite the scientific success of the previous generation Big Four, Hubble, Compton, Chandra, and Spitzer, JWST was so expensive, $9 billion over a $1 billion budget, and so delayed, 14 years late, that future telescopes face an existential programmatic challenge. Programs get more expensive, more infrequent, and have ever greater challenges maintaining institutional knowledge. Meanwhile, achingly slow development over years or decades drives up cost, further inhibiting future acceleration. Graph showing steady slippage of schedule and growth of cost on JWST. Image. Look no further than the most recent Astrophysics and Astronomy Decadal Survey, published November 2021. In it, the proposed new great observatories for next-generation telescopes to be launched in the 2030s was considered too ambitious, in favor of a more expensive, more delayed, less ambitious, descoped all-in-one hybrid telescope to be launched in the 2050s. Two telescopes, LUVOIR and HAB-X, focusing on different aspects of habitable exoplanets have endured the indignity of an arranged marriage into the Habitable Worlds Observatory, cutting ambition, multiplying complexity and schedule while compromising scientific utility. Current PhD students will be nearing retirement by the time these missions fly. We are literally up against the limits of the human lifespan as we scratch for crumbs against a backdrop of the greatest levels of technical knowledge and wealth that our species has ever attained. There must be another way. The new Great Observatories, RIP. How does Starship help? Starship is designed to launch at least 150 tons to low Earth orbit at exceptionally low cost, with a launch cadence high enough to ultimately deliver over 1 million tons per year, roughly 2,000 times the current global launch volume. This represents a transformation in human logistical capacity in space. Why does this help telescopes? One of the reasons JWST was so expensive was that in addition to being exquisitely precise, robotically operated in a pitiless vacuum, and parts of it at cryogenically cold temperatures. It also had to be feather light and capable of folding up like origami to fit within the Ariane V payload fairing. Starship has mass, volume, and launch capacity to spare, relaxing these engineering constraints and significantly simplifying design. Starship can allow greatly reduced space development costs, provided that telescope and instrument designers internalize its capabilities and reallocate resources towards rapid iteration on a production line style program. This can break the dismal spiraling cycle of programmatic bloat, slipping schedules, and eye-watering costs. JWST represents the pinnacle of what this sort of highly contingent, highly complex, extremely expensive development process can achieve. It is time to take another approach. The Starship internal fairing diameter is 8 meters. A Hubble-style telescope with a monolithic mirror could quite easily match JWST's 6.5 meters, and without any complex deployment procedure. Alternatively, a JWST-style folding process could extend the mirror up to 15 meters, though it would definitely be cheaper simply to engineer a 16-meter one-off Starship fairing and launch it as a monolithic instrument. The largest of the next generation of ground-based observatories is the European Extremely Large Telescope, ELT, at nearly 40 meters, which pushes the limits of mechanical construction under Earth's gravity. The mirror assembly can tilt up and down to follow a target as the Earth rotates, but as it does so, gravitational forces change throughout the structure, causing it to flex enough to disrupt the image. Building a 16-meter diameter space telescope and launching on Starship is a fascinating idea, and we should absolutely do this 10 or 100 times, why not? But Starship is so capable, we should ask ourselves what the true physical limit is to our ability to build enormous telescopes. Assembling colossal mirrors in space sidesteps the gravity and atmosphere problems, so it is time to accept that the scope of our ambition exceeds the scale achievable on the surface of any planet, and use Starship to build transformational observatories in deep space. A basic schematic of the monster scope, composed of multiple free-flying parts. The monster scope has a mirror diameter of 1 kilometer, an unthinkably enormous span of glass enabling us to examine the features of nearby exoplanets with the same detail anyone can see on Jupiter with a pair of binoculars. This mirror is self-assembled in space from thousands of 8-meter hexagonal segments, each an independent free-flying satellite and derived from the Starlink satellite design to keep costs and mass low. A self-assembling space mirror has been studied in detail with the AREST concept, but the monster scope takes it to its logical extreme. These segments are stacked in the Starship fairing and launched by the dozen into deep space, for example Earth-Sun L2, the same gravitational island used by JWST. Once in position, they autonomously maneuver to the growing mirror, dock with adjacent segments and, once locked in, independently align their mirrors. A free-flying mirror position sensor, blue cylinder above, flies at twice the focal length to provide the feedback needed to dynamically tune the shape of the mirror. This is a standard procedure for making mirrors and relies on interferometry. Some of the usual design constraints on focal length don't apply in this case, as free-flying instruments in the imaging plane can be positioned beyond the radius of the mirror without obstructing the image. For the purpose of this post, I imagined a configuration with an exceptionally long focal length. The long focal length relative to aperture minimizes off-axis aberrations, which grow roughly as the square of the angle relative to the optical axis divided by the focal length. The assembled and growing mirror forms a hyperbolic shape, which creates a larger focal plane covering perhaps 10 degrees of the sky. While the mirror can be turned, it will primarily be set up facing a particular set of chosen targets. Nearly all the known extrasolar planets were discovered by the Kepler mission, which itself had a 10-degree field of view. There are worse ideas than following up the Kepler exoplanets with a mirror 700 times larger. The light from thousands of stars comes into focus at the focal plane, which occurs in a thin disk roughly 500 kilometers from the mirror and 100 kilometers across. Between the stars there are also opportunities to image and study distant galaxies and perhaps the first generation of stars, which are yet to be directly observed. Dedicated free-flying instruments and their host spacecraft, gray boxes above, can navigate within this region. This approach allows the independent design and parallel operation of both the mirror infrastructure and the sensor payloads, increasing access to valuable science. While one free-flying satellite and large adaptable mirror may be extremely expensive to produce, thousands allow the production process to be greatly improved. This process, called the learning rate, describes a property of manufactured products whose unit cost drops by a fixed percentage per doubling of output. For products of this nature, a learning rate of 30% is conservative until we encounter fundamental material cost limits. The similarly sized mirrors, cast in glass, for the giant Magellan telescope, cost $20 million each. Starlink satellites are on the order of $100,000. Power electronics for piezo adaptive optics are also about this price. Putting it all together, let's baseline the first mirror satellite at $50 million, not including development costs. Since nearly all the tech being used is high TRL if not off the shelf, we can greatly reduce development costs. In particular, Starship's generous upmass capability greatly reduces the need for exponentially greater spend on incrementally lighter components. The full 1 km telescope will require about 20,000 mirrors. With a 30% learning rate, we get down to about $300,000 per mirror and a cumulative cost of about $10 billion. The same as JWST, only 150 times wider and 22,000 times more sensitive. Including launch costs on a similar curve increases total cost by about $2 billion. But why stop there? The mirror's shape and scale is adaptable. We can continue to grow this mirror, or build another like it to focus on a different target, as the program progresses. The angular resolution of an aperture is a simple ratio of the diameter of the aperture and the wavelength of light being observed. Given by the formula 1.22 times the wavelength divided by the diameter of the aperture. Intuitively, this can be thought of as counting the number of photons of a given wavelength which can be lined up across the span of the aperture, with that number corresponding to the number of distinct details that can be independently distinguished from one another. Thus, increasing the angular resolution requires either observations at a shorter wavelength, or observations with a larger aperture. Since the apparent or angular size of objects decreases linearly with their distance from the observer, the spatial resolution that can be achieved by an aperture is its angular resolution multiplied by its diameter. The closest exoplanet is Proxima Centauri b, at a distance of 4.2 light-years. It is believed to be approximately the size of Earth, i.e., with a diameter on the order of 10,000 kilometers. A 1 kilometer aperture provides a spatial resolution of around 22,000 kilometers at this wavelength, not quite sufficient to resolve the planet as anything but a point of light. The situation is even more marginal for the Kepler planets, which are at distances on the order of 100 to 1,000 light-years. At the upper end, that's a spatial resolution of about 5 million kilometers. However, it's worth pointing out that 5 million kilometers is well below 1 astronomical unit, meaning that while a 1 kilometer aperture wouldn't really be able to take pictures of exoplanets, it would very easily resolve exoplanetary systems. Since we're currently limited mostly by the transit method, we're blind to something like 99% of exoplanets. We can't see the exoplanets whose orbital planes don't produce eclipses. The monster scope would enable us to conduct an extremely thorough census of exoplanets, detecting basically everything out there, including, in particular, actual Earth-like worlds, i.e., rocky worlds orbiting in the habitable zones of G-type stars, which are basically impossible to find via either the transit or the radial velocity methods. Even with single-point detection, we can still resolve surface details by measuring detailed spectral information over time. The planet's day and night rotation and yearly orbit brings different parts into view under different light conditions, which sophisticated modeling can invert to further increase the resolving power of the telescope. Furthermore, since 1 kilometer is an absurdly large light bucket, it can scoop up a lot of photons. Light gathering power is a function of the area of the aperture, so this goes up as the square of the diameter. Since apparent magnitude is a logarithmic function, every doubling of aperture diameter increases the sensitivity by 1.5 magnitudes. JWST can apparently detect objects with apparent magnitudes of around plus 30, so the monster scope should be easily able to detect objects with apparent magnitudes of plus 40, roughly 7 size doublings. Assuming a star-planet delta magnitude of about 23 mag, i.e., the Sun-Earth case, the monster scope would then be able to detect exoplanets around stars with apparent visual magnitudes of 17 or below, which should be a very large number of planets. There are about 157 million stars with V less than or equal to 17 in the Gaia catalogue, so assuming roughly 10 planets per star, that's on the order of 1.5 billion exoplanets. Restricting this to planets in a 10-degree field of view aligned to the galactic plane, it's still 40 million planets. Finally, there's nothing set in stone about the 1 kilometer aperture. Even more angular resolving power can be added by adding free-flying outrigger mirrors, albeit with non-trivial alignment and wavefront management issues. For example, this mirror shape provides an image point spread function, calculated using the Fourier transform, of the wide fringes are the resolving limit of the individual small disks, while the inner fringes correspond to the resolving power of the solid inner disk. Finally, the central peak is the resolving limit of all the mirrors combined, corresponding to the diameter of the entire array. This particular configuration is given just as an example. Numerous further optimizations are possible. I particularly like the idea of running steadily more advanced instruments as the size of the mirror is increased, enabling improved follow-up studies of interesting nearer exoplanets and at the same time, detecting millions of others at greater distances. Whenever we build a new, more powerful telescope, we discover new and strange and wonderful things. Things that have been there all along, but invisible to us with our puny eyes and primitive technology. There's an old joke that the quality of the astronomer is proportional to the size of the telescope. Instead of wasting the careers of scientists, engineers, and technologists on 3 decades of dead-end paper studies that teach us nothing about our universe and dissipate what little practical space telescope knowledge we already have, we can raise the scope of our ambition and build an exquisite instrument at the limit of physics, capable of imaging alien planets as though they were as close as our moon. The monster scope is designed to resolve features on the surface of exoplanets. Thousands of known exoplanets planets can be directly imaged, their continents, mountain ranges, and river systems studied from many light years away. Seasonal variations in plants and animals, if any, will be visible. Spectroscopic analysis of discrete surface features on each planet will tell us more about their geology than we knew about even Mars just 40 years ago. While it is true that aspects of this vision require new technology and are unprecedented in scale, let us also remember that the Starlink constellation was science fiction for 35 years and now has 6,400 active satellites serving 4 million customers. Starship represents a huge step change in our ability to execute missions in space, and we should grasp it with both hands. Humans have stared into the night sky for 10,000 generations and wondered, are we alone? Are there other worlds out there we can live on? Can we understand general relativity well enough to enable interstellar travel? The Starship-enabled monster scope may answer that question within our lifetime.